Okay, so welcome to the computer graphics rendering class. So today we're going to talk about shadow mapping, and then towards the end we'll maybe pick up a little bit where we left off on Thursday, where we were talking, we wanted to implement something where you can maybe drag and drop or drag the screen so you can rotate the object. Okay, so just real quick, due dates on Blackboard. Let me just show you what's going on there. I think I updated all the homeworks and everything, so wait for this to load. We want 481. Okay, so I think everybody's already turned in ray tracing homework. The next part, well, I guess the two that are kind of still out there, or maybe three that are still out there, the real-time rendering. So this is where you use a real-time renderer to create an interactive 3D scene, and then go ahead and write a vertex and fragment shader to shade it, and then submit a one-page report, kind of like before. We have a screenshot and a link to your program, and then also submit your source code for the vertex shader and fragment shader, so I can see what you decided to do. And the next homework will be the shadow map. So if you're working in a real-time renderer and you have the ability to kind of do shadow maps in there, then what I want you to do is and what I'll do is I'll include a copy of the shadow map homework that not the homework, but the demo I'm going to show today. It's a little bit older code that I wrote a long time ago, but you can kind of get in there and tweak some things if you want. Or, you know, if you're already working with Unity or something and you want to just play around with the main point is to get you to experiment with how shadow maps work and what you can do with them, in terms of, because it's not like a plug and play technology, as I will show you today. Okay, and then just include a few different images where I can see that you were adjusting different settings and playing around with it. Okay, and then I can't remember if everybody did this one, but the student choice homework is also due, where you can kind of pick a variety of things that you'd like to do, but you know, just kind of spending more time doing computer graphics rendering. Okay, so it's pretty flexible. You can make a game, experiment with different kinds of BRDFs. So if you're like using a 3D program, you know, maybe make an image study like, I'm going to play around with the Blinn Phong BRDF and then adjust different settings, and you know, so just show me what you kind of did there. Okay, and then the game competition, that's technically not due until the day of the final. So I think so, yeah. So what's cool about this, it depends if you get excited like this, at the end of the month is the Ludum Dare, the actual 2019 one for the spring. So if you want to participate in that, it's starts Friday the 26th and goes through Sunday afternoon. It's a 48-hour make your own game. So this is perfect for this. I couldn't have timed it better. Okay, all right. Okay.
26 is my move-in day with my girlfriend. Yeah, so we're going to spend the whole weekend moving our stuff in.
Oh, okay. Well, then do 1 hour game jam, right? That's yeah. This one's coming up here. Ludum Dare. They're doing the theme slaughter right now, so this is a good this is a fun one to get involved with. Oh, I guess they're not doing one in the summer. The next one's in October. Oh, they're only going 2 times a year. Okay. That's fine. Cool. All right. Anyways, this is fun. The last one, I forget what the last theme was. But the way this works is people submit themes, and then you just say no, this one, you vote for the ones you want, basically, to keep going. So it appears that oh yeah, there's a lot. This guy went through almost 4,000 themes. That's funny. Okay. Anyways, like you know, so in the end, like, you don't know what it's going to be until an hour before. I want to say an hour before everything starts, and then where they let you know exactly when it starts. But you know, so if it's like 2 connected worlds and you make a game based on that idea of 2 connected worlds, or color changes everything, right? Make a game. I think it's fun when you have some kind of, it kind of helps creativity, I think, because you're not thinking about, I could make a game about anything. This one kind of like focuses you a little bit. You know, you make a game about something. Okay, it's still hard. Okay, so
for that one, you want us to make something with those themes from 2018 or?
Right. Yeah. So I want to, let's see here, the previous ones. So if I go, see here, for 43, this one was for December. Sacrifices must be made. That could be fun. Okay. The one in August was running out of space. Okay, running out of space. I should copy and paste this. This would be, or combine 2 incompatible genres. I should probably just do that. And I'll edit it when I know about the other one. Okay, so let me go to the HTML. Okay. Running out of space. Sacrifices must be made. And you know what's nice about this? If you're like really, I have no idea what to make, then you can go look and see what everybody else made for all the old ones and kind of get some ideas like, oh, that would be fun. Okay. Let me make that emphasis. So we don't know what that is. It's not. Okay. Submit. Okay, so that one's in there. So due dates. All right, we're talking about due dates. I wish it would tell you what the due date was on the homework, but like when you look at the whole.
Yeah, there's a due date status.
I mean, I know I can look it up. So 420, the real-time renderer is due this week, and you know, if you're trying to stay focused a little bit, what I would do maybe is try to work all of this together. Like, there's no reason why it has to be like a completely brand new, different, you know, thing. Especially if you're working up towards the game competition. You know, all this work can be contributing towards that. Okay, shadow maps might be a little bit different, but okay. So maybe there is a way of. I don't know if there is a way of. I'm just looking at the. Okay, the shadow map one should be due the following weekend, which is what, the 27th, or the 28th. So I guess technically the I would probably combine whatever you're doing for the student's choice to kind of go with the game competition, because those are all due like by the day of the final. So just work all these 3, work them all together, and it won't be hard. So I'm trying to make it as streamlined as possible, because I know that we were kind of delayed a little bit with the homework due dates, but if you combine them, then I think they'll be it won't be so bad. Okay, any questions on the homework? Okay, All right, so let's go ahead and talk about shadow mapping. So shadow mapping is one of two different algorithms, or two real-time algorithms for doing shadows in a real-time rendering engine. Okay, so we already learned about path tracing, ray tracing. You know, if you want to find out if something's in shadow, so we'll just have like, so we'll have our light over here. Okay, and if we know that this guy is in shadow because this light here. You have a shadow caster and you have a shadow receiver. So sometimes you'll see something, shadow cast, or it'll cast shadows, and then something that receives shadows. Okay. And the reason why you'll see that sometimes is because it's nice to be able, you need to have a lot of control over these algorithms, whether something should cast shadows or not, because that can impact the whole performance or the whole ability for the your 3D renderer actually render them in a decent way. Okay, so one of the methods is called shadow volumes, and the hybrid topics video for this week will be on shadow volumes. Okay, so we're going to spend time on shadow mapping, but I do want you guys to know what shadow volumes are. And just to give you just a quick overview, is you will construct a volume, and you basically count. You can use something called a stencil buffer, and you can basically count the number of times you enter into the volume and leave the volume. Okay, so in this case, you'll create, you know, this will represent the volume. Okay, it starts here and goes. But you can count when you go in, and you can count when you leave. Okay, so then so over here we're in, and over here we can see, well, we're in the shadow volume. So now that one's going to be in shadow. Whereas if you had a light, like let's just say maybe this box over here, and you're trying to view this scene, you're going in, we're going out. So you know, just by the number of times you went in and out, that now nothing over here is in shadow. So that's one way of doing it. Shadow volumes, where you just kind of keep track of whether you're inside the volume of shadow or you're not. Okay, this one is more complicated in the sense that you have to build these volumes. Okay, so it's not like a just do it kind of task, you know. You have to put that inside of your program to construct these volumes. And then sometimes, depending on if you have overlapping shadow volumes, then it can act a little funny. Anyway, so we're going to talk about that on Thursday's Hybrid Topics video. But the other way, and I guess I should mention that Frank Crow invented this one. Let me make sure I have that correct. In 1977. Let me just make sure. Let me go to my research. Oh, wrong one. This is the origins of the teapot. That's a good article too. I'm looking for the other. We'll try our other friend. Yeah, okay, so I was right. That was shadow volumes. Franco invented shadow volumes. Now, Shadow mapping was also invented in the 70s. And we'll just open this paper up. It's probably Williams, Lance Williams, in 78. Okay, so Lance Williams made this one in 1978. Okay, those are two decent papers. Okay, shadows. Now, you remember what happened in 1980, 1981? What famous paper did we look at in this class? The one that kind of solved shadows. The ray tracing one. The ray tracing paper by. Why do I keep getting names? I keep thinking of Blinn, but it's not Blinn. It's I don't think the coffee's working this morning. It's I'm struggling. Okay. It's over here somewhere. This is embarrassing. Whitted. I couldn't think of Whitted's name. Okay, Whitted ray tracing, 1980, right? And remember that solved the reflection, refraction, shadows all in one go. Okay. Let me go back to week 14 here. Okay. Okay, so Whitted ray tracing kind of solved these problems. But remember, we said that before nobody would do ray tracing as a practical matter because it was so slow. Like, I mean, yeah, it was. You could do that, but it was so slow. So instead, we're focusing on real-time methods. So a lot of the 1970s is how do we do rasterizing, rasterization, draw polygons. Drawing polygons is easy. We know how to put pixels on the screen. We know how to figure out where the triangles should go on the screen. Okay, whereas ray tracing, it's like, let's just pretend we don't even know where the triangles are, and we'll cast rays until we eventually find the right one, okay? So along with the Z-buffer algorithm, okay, the Z-buffer algorithm is what enables this particular one to work. All right. And so the way that this works is that we want to render the scene from the viewpoint of the light source. Okay, so we want to render the viewport from the viewpoint of the light source. So we have a texture map here. And we're going to render the Z-buffer, essentially, for this scene. So if we're taking a look at, let me redraw the camera here. Okay, so if we're looking at this object that's in shadow, we can use the shadow map. This is the shadow map here. To determine whether or not this object is visible to the light source or not. Okay, because what happens, and let's just say we're interested with this pixel right here. Okay, that's the pixel we're interested in. Let me just make sure this is pointing towards the board. Okay, so we're interested in this pixel right here. So we can see that if we were to have rendered this from the viewpoint of the light source, say it's this pixel, that this one is closer than this one. Okay, so we know that if we were to draw the camera up here, that all this would be lit. We would never even see this surface because it's hidden. Okay, and so what we can do is we can say, well, what did the light see? So then we look up this pixel inside the shadow map, and we can see that the Z value, we'll call that Z1 and Z2 here. We can see that Z1 is closer than Z2. So in this case, because Z1 is less than Z2, we know that that is in shadow because this is not the closest point to the light source. Okay. Now let's pick another pixel. Let's say this pixel right here. We'll call this Z3, and let's just say that that represents that pixel inside of the Z buffer on the shadow map. Well, we go and we look up what this value is, and because this technically should be the same Z value, because there's nothing blocking this light, then we'll call this one, we'll say that Z3 is less than, we'll call that Z4. So Z4 is right there, Z1 is right there. Okay, so because the shadow map value, in this case, it's this exact same pixel, okay? So they should be approximately equal. So we want less than or equal. So as long as it's closer than or further, I guess, we want this one to at least be closer, because if the value that was stored in the Z buffer is all the way back here, then it's still closer. So that means it's fine. And there are reasons why potentially we don't have a front-facing polygon in the Z buffer, and we'll talk about that later on. But the main point is that as long as the value that we're seeing from the camera is closer than the one we're seeing in the shadow map, then we can go ahead and light that. Okay. Now, there's a lot of nuances that go along with this, but does anybody?
So we can measure the distance in terms of camera?
We're measuring in terms of distance to the light. Distance to the light. Okay. So I guess in the grand scheme of things, we're calculating two different Z values. Okay. So let's take a look at that real quick.
So is that the Z3 is less than 4 Z4 or?
Yes. Let me make that a little more. Let me kind of draw like a different kind of diagram to kind of show what's going on. Okay, so this is, I guess, more or less how it's working. So I'm not going to put it there. So part one is render shadow map. Okay, so in which case we're going to render this image right here. We'll render the image. So everything that's getting drawn is getting written into there. So let me find a different way of using the subscripts. So we're going to say, and the reason I say that is because we're trying to draw another image, right? And it has its own Z buffer, right? The camera. Okay, so we have the light, and when I say light, we're just going to call this the light shadow map, or instead of calling it shadow, I'm going to call that depth map. All right, because shadow, you kind of think, is it pre-encoding whether it's visible or not? Okay, so we're going to call it depth map because that's what it's storing, depth values. Okay, and then we have the, I don't want to call it a camera, but we'll just call it the frame buffer. Depth map. Okay, so the first part we get this the light step map. Okay, this is different than the frame buffer depth map, which we're doing over here. Okay, because this one we're just trying to make sure that, you know, this pixel doesn't get overwritten by this pixel. Right, so we're trying to make sure that that's separate. But what we need to do as a separate process is we need to say, well, let's call this P. Okay, that's our position for this object over here for the receiver. And so I guess I'll call it P receiver. So we need to calculate two coordinates. Okay, first of all, we need to figure out we're going to figure out, well, what is this from the viewpoint of this camera, right? Okay, and that has to do with drawing this frame buffer. But then we have to do another one, which is from the light. Okay. So each one of these is going to have basically two different transformations, two different ones. And really what I'm trying to show you is that they're two completely separate values. They have nothing whatsoever to do with each other. Nothing. Okay? So the only thing that's similar about them is that they follow the same general pattern. Okay? So we have to multiply our projection matrix, right? Like that'll be our perspective projection or orthographic, whatever we're drawing our 3D scene as. So we have a projection, then we have our camera matrix, or view matrix, which if you remember from previous classes, an inverse matrix, the inverse camera transform. Okay, and then we multiply it by P. Okay, and that's how we get our position in the frame buffer, how we're going to draw that. Now, we're going to see the same pattern over here for the light. Okay, but if you think about it, this whole transformation over here is designed to put pixels into this frame buffer. Okay, and when we render the shadow map, we're basically doing this exact same calculation right here, except that the camera is the light. So we use the light matrix. The inverse of the light matrix is like a camera matrix for it. Okay, so now we want to after we've drawn the shadow map, we got a bunch of z values in here, and we would like to compare what this one's supposed to be. So we're basically doing all of the steps ourselves in terms of, well, what is the actual x-y coordinates inside this texture map that we're going to look up. So what we do is we calculate the projection matrix. Okay, and I'm going to call that L, because this is a matrix, whatever we use to render the light map with, whatever projection matrix we use to render the light map. So if we said we want a 90-degree field of view or a 45-degree field of view, that's what that's encoding. Okay. The second thing is whatever our world matrix was for the light, we want the inverse for that. Inverse world matrix. Then we multiply, well, I guess what I haven't mentioned is the fact that we have the world matrix for the receiver, but how about we just do this? Okay, so our receiver, we're talking world coordinates here. So if this object we had to move it around the scene, then we go ahead and do that with its world matrix, and then we multiply it by, okay, P receiver. So they more or less have the same pattern, but what this is going to do is this is going to allow us to figure out what where do we need to pull the texture coordinate? What is the texture coordinate for this texture map? Because that's basically how we're using it. Okay? Okay. And the whole idea then is to figure out, well, what z value would we have written into the depth map over here? We want to find out what z value is. Now there's another step in here that we have not added, and that's called a shadow matrix, a shadow bias matrix. Okay, and let's go ahead and take a look at that real quick.
What's that P for the P receiver?
Sorry, over here?
Yeah. What's the P?
Oh, so we're talking like this coordinate here. That whatever the vertex or position, the fragment, that's the world coordinates of the object that we're trying to, the point that we're trying to shade and figure out if it's in shadow or not. Okay? All right. So, the next step, okay, is we need to add this shadow bias matrix. Okay, so here's what the shadow matrix looks like. We're basically scaling all the x, y, and z components by 1/2, and then translating them all by 1/2. Now, why do you think that we do this next step?
Otherwise, you get artifacted.
Nope. Nope, not artifacting. Okay. The reason why is because when we do our projection, remember we were talking about the Cartesian coordinate system and texture maps last time, and the whole idea of, you know, you have your x-y axis, you know, y is going positive, x is going positive. When you do your projection, right, when you're looking at when you're drawing your scene, where do you expect the origin of the scene to be? On your screen, where do you expect that to be? For the texture, yes, but on the screen, right? If I was going to put an object like the teapot smack dab with an identity matrix, where should we expect to see that on the screen? In the middle, smack dab in the middle. Okay, so because what happens is that when we're drawing, right? We're drawing like this. Okay, so the origin's right there in the middle of the screen, and but the problem is that if we don't use this bias matrix, then we don't properly, you know, when we're looking at our shadow map, we need the correct coordinates in the shadow map, and the coordinates go from what to what? 0, 0 to 1, 1. Okay, so here's what's going to happen. If we had let's say we had the coordinates -1, -1. I'm just going to pick 0 here, just for convenience. Okay. If we multiply this matrix by this vector, we're going to get 1/2 times -1, so that's -1/2. All right, times 0 plus 1/2. So we'll get 0 for the x coordinate. Okay, and then for the y coordinate, we'll get 0 times -1 plus 1/2 times -1, so that's -1/2 plus 1/2. So we get another 0. And same thing for the z. We're just ignoring z right now because we're thinking x, y coordinates. Okay, so we're going to have 0, 0, 0. I guess if we have minus 1, I'll just put this here. So if we throw in negative numbers on our bias matrix, then we're going to get minus 1, minus 1. So we're going to get 0, 0, which is the lower left-hand corner of the texture map. And if we throw in 1, 1, 1, so that's the other side, then 1/2 times 1 plus 1/2 is then 1. 1/2 times 1 plus 1/2 is then 1. So this maps to our texture coordinates. So now we can use this to map directly into the shadow map. If we don't do this, the shadow map, we're only going to address this part of the shadow map. Something like that. We're going to incorrectly address the shadow map, and then what's that going to do with the whole algorithm? It's going to, hopefully, ideally, what we're going to expect is to see some kind of shift in our scene where it looks like objects are casting shadows in other areas that we didn't expect. Hopefully, we're going to see what happens if we don't have it on. So we turn it off or turn it off. Okay, just because it helps to kind of see what if you forget to do something. Okay, so the shadow bias matrix basically is designed so that we are able then to look directly into the shadow map without having to, because if we're talking about objects that are suddenly on the negative x-axis or the negative y-axis, suddenly we can't shadow map them. And that's basically why that is. Okay, so we're going to render the frame buffer object from the point of view of the light. Then we're going to, when we're rendering the scene from the camera, project our coordinate P as if we were looking at it so we can figure out what got written into this texture map, and then we can compare our z-values. Okay, and this is not to be compared with what is the distance from the camera to the point, because it has nothing to do with this calculation. Okay, so let's look a little bit at the code here. So here's a small snippet. So from the point of view from the vertex shader, we're going to pass in a few extra matrices. So the shadow matrix, the projection matrix, the light's model view inverse matrix, and then the world matrix for our points. So we move everything to world coordinates, and then we basically move it as if we're going to render the scene from the viewpoint of the light source. Okay, so then all we have to do is then we say shadow matrix times the projection matrix times the model view inverse matrix for the light times the world position, the world matrix times the position of our object of our drawing. Okay, and the camera is going to look basically like, okay, camera projection matrix or times the camera matrix times the world matrix. They'll look more or less the same, but the idea here, or I guess the key concept, is to remember what that inverse matrix is doing. So so what does the inverse matrix do? If we have a world matrix,
it's putting it in terms of the lights.
Right.
It fits that.
Right. So I guess one way to think about this, just in general, there's a really important concept about inverse matrices. Let's just say that each one of us in the room have our own matrix, right? So Rajan has a matrix that says she's sitting in that chair looking in this direction, and Kim has a world matrix that puts him in his chair looking in his direction. I have my matrix sitting here in the front of, or standing here in the front of the class looking out towards the class. And let's just say that I want to, we would like anybody to be able to see exactly what Rashan sees or what Kim sees or what I see. All we have to do that, right, is we move them into world coordinates. Then we take your matrix and we invert it, and we multiply it against their matrix. And now we basically put them in your local space, right? In your local space. So it's a very nice trick. If you just think that, okay, if I need to see something from the point of view of somebody else, all I need is their world matrix. You take the inverse, and now everything can be viewed as if I'm looking from their eyes. Okay? And that's exactly what this inverse light matrix is doing. It's basically saying, I want to look at the scene from the viewpoint of the light. So I use the inverse world matrix for the light. Okay, and the same thing is happening with the camera, although a lot of times when we say like a view matrix, it's already kind of implied that it is an inverse matrix. Okay, but it's not obvious because nobody just sits down and just says it right out that this is what this is. Okay, but this is really what it is. Okay, so from the standpoint of the vertex shader, it's not really too complicated. We just basically are just, it's almost like we're trying to draw two objects at the same time in two different frame buffers with two different points of view. Okay, so the next part in the fragment shader, let's just say we have already rendered our texture, and last time we already did render to texture in terms of we're just, instead of rendering to the main screen, we can render to another texture map. So in the fragment shader, we are basically saying, okay, let's, whoa. Oh, that's right. I forget, if you double click in the window that you'll get, it'll try and take you to the source code. Okay, so now we want to find out if we're in shadow or not. Okay, so assuming that we already know, I guess, what our z value is and the texture coordinates, we can then compare, we can grab the sample for the shadow. Okay, so in this little bit of source code, there's a few things going on. So let's just take it from the very end here. Okay, this is returning 0 or 1. So what I'm trying to, this function I want to say, am I in shadow or am I not in shadow? Okay, in shadow, not in shadow. So the next thing is we need to look up the z value for our depth buffer. Okay, so our coordinates, in this case, is this confusing to have p and v over here? Maybe I should just rename those. I was taking them from another let me rename that so it's a little bit more. The reason I have P here is because STP. Okay, because I was using the trying to use the texture coordinate names. Okay, but I think it's maybe a little bit confusing. I'm going to call that Z, and I'm going to call that XY. No, ST. And yeah, I think that looks better. Okay, hopefully this is maybe a little less confusing. Okay, so we're passing in the Z value. This is the one we just calculated. This is the one we're trying to test. Okay, we don't know if this is closer, farther. We don't know the answer to that. ST is the coordinates inside of the shadow map. So we say, let's look it up inside the shadow map and determine whether or not it's in shadow or not. In other words, compare the Z values. Okay, so this last one is an offset. Okay, let's just pretend the offset is 0, 0. Okay, you can see over here what we're doing is we're saying, let's take whatever is inside, let's take the ST coordinate, the shadow map coordinate, and add an offset to it. Okay, so in other words, if the, I got a lot going on here. So if this was our shadow map, okay, and let's just say inside here we're just looking at the different pixels. Okay, let's just say the ST is right over here. We're going to see later, we may want to add an offset to it so that we can take a look at maybe the neighboring pixels and compare Z values, kind of see what's happening around the local area, because that might be important. Okay, so this is the shadow map. Okay, and just by way of blowing this up, right? You know, a lot of times we think of, you know, red, green, blue, alpha, right? We think of RGB texture map. But the depth channel obviously is just one channel, right? One channel because it's just holding depth values, okay? So what component do you think we're going to address that? How do you think we're going to get the Z value out? What component do you think we're going to take a look at? Get this VEC4 out. The green, the blue, and the alpha are all going to be 0 because there's no data there. Only the red channel will have the Z value in it. Okay? All right, so that's why I have that .r at the end. Because it might be tempting to do this, right? Because we're getting a VEC4 out, and we're saying, well, what if we use Z subscripts to access the Z? What's going to happen? What's that? There's nothing. Yeah, it's accessing the third channel, which is 0, because this is only a one-channel texture map, which is stored in here. Okay, so this is another source of mistakes. It's like, oh, I'm comparing the Z values. Right? And you're thinking if I'm looking at the depth map and I'm looking at .z, then I'm looking at the Z value. No, you're not looking at the Z value, you're looking at what has been the blue channel, channel number 3. Okay, so when you're working with these texture functions, just be mindful that it might be returning a VEC4, but you have to know where the data is stored. Okay, so that's why we look at the R channel. Not because we're looking at red, but because the Z value is stored in channel 0 or channel 1, 1, 2, 3, 4. The first channel, there we go, we use ordinal numbers. The first channel, and which is red, okay? So I think I may have made that mistake once in the past where I'm looking at Z, but why isn't, it was just my misinterpretation of how all this stuff works, okay? Because the way Texture 2D works. Okay, so Texture 2D, I'm accessing the depth texture. I'm looking up pixel ST, that's the coordinates, right? ST goes 0 to 1, which we use the shadow bias matrix to offset everything, so we're looking only in the texture map. I do this little special case where you have to be able to decide what if the coordinates I passed in were outside of the texture map? Well, this is the decision you have to make. Should it be shadowed? Should it be lit? Right? Because if I return 0 is in shadow, like if I look outside the texture map, what is that area in shadow or is that lit? That's a choice. Okay? They go to 1. But why is it 1? It's 1 because that represents the far plane. Right? 0 is the near plane, 1 is the far plane. So when we clear the depth buffer, so it's kind of interesting. You just have to kind of know how these buffers are handled. If we're clearing the color buffer, we normally think, well, we want to set it to black. So we set it to 0s. When we clear the depth channel, we're trying to set that to be far, right? All the way out there. So we set it to 1. And every time we want to write to the depth buffer, we check, is my Z value less than whatever is in the depth buffer? Well, if your numbers go from 0 to 1, yeah, it's always going to be less than. So you can just, that first layer that gets drawn in always overwrites whatever's in there. So that means that if you, this matters because, maybe we can take a look at this. If we set the far plane on the light to be like over here, this is 1. So if we calculate this z value, this is going to be greater than 1. And what's going to happen is it's going to look like this is in shadow because this is further out. This is greater than the far plane, which is 1. So we'll see that you may even have to add a check to make sure is the value that I just got from the depth buffer already 1, like from the shadow map. If it's already 1, that means nothing was even drawn there. That represents infinity. So it's not in shadow because it never got there. Okay. Sometimes this has to be experienced, so we're going to take a look at that. I think I named that function wrong. I think it's supposed to return is in shadow. I think it's right. We'll see what happens. Okay, we'll play with it. Okay, so that's the first step, right? We have our function is in shadow, which basically return 1 or 0 depending on whether or not we're shadowed or not. And here's where we do our test, right? We say if keep double clicking. Okay. We say if whatever was in the z, if the z value inside the shadow map is less than the value that we're checking, then we know that we found something closer. In other words, we're looking to make sure that our z values are less than, we always want something closer, right? So this one over here would be less than whatever's stored in here, because technically, hopefully 1's back here, but we'll see. Shadow maps are finicky. Okay, you have to work with them, and if you decide that you're going to get too greedy by like, I'm going to make the most generic shadow map ever, then you'll see it doesn't work very well. So you normally have to tweak the shadow map so that it works. Okay, now what we haven't talked about yet, remember we were talking about the depth buffer not too long ago, and we were talking about how the values are distributed logarithmically, right? So that you have most of your values are stored between your close values are stored between 0 and 0.9-ish, because the log curve, right? So then at a certain point, then you only have very limited precision going out, right? So if you set that near plane too close to the shadow map, all your precision is going to be up here, and these values are going to, because what we're going to do is we're going to take that number, we're going to turn it to, minimally speaking, a 16-bit number, right? We talked about that a little bit. If your depth buffer is 16 bits, you have 65,536 possible values you could have. And logarithmically speaking, if you set this too close, really a lot of you may only have about 6,000 values of separation. Well, herein lies a problem. Okay, that is really going to pop up when we're comparing our shadow maps, because when we're looking at it from the viewpoint of the camera, we have this point, if it was, especially the ones that are in shadow, this one probably doesn't matter, but the one that is being shadowed does matter. What's going to happen is that we like to think of the surface as being smooth, but you end up getting this discrete edge that happens where I'm checking over here, like my z value, and we're like, yes, I'm closer, right? Because this represents what the z buffer is doing. But then you check this surface, and now it's further. Okay, so this is, I'll call it an S for shadow, L for lit. Okay, so even though this surface maybe technically should be lit, okay, like this one over here, and this is if we render. So this one is an easy case, okay. But if we render the shadow map over here and we're trying to render this box, this is what's going to happen. And even if it's lit, we're going to see this pattern pop up. This pixel is going to look like it wants to be lit. This pixel is going to look like it should have been shadowed, even though technically it should be lit, right? If we're just rechecking the same values, okay? Then this one will look like it's lit, and then this one will look like it's shadowed, lit, shadowed. So this is called surface acne. Surface acne. Okay, and one of the ways to fix surface acne is to add a small bias. So if you notice over here, I have this epsilon, and I say z minus epsilon is greater than my shadow sample. And so what I'm basically saying is like, okay, I know that there's some inherent problems with the depth buffer, so let's just pretend, and you notice how I'm doing z minus epsilon. It's like we're saying, let's just pretend that my surface that I'm trying to check against the shadow is really more back here, so that we don't have that issue. Although sometimes you do get an issue. Okay. So we have this epsilon value in here that we're checking against to kind of help guard against these imprecisions in the depth buffer. And now, the only problem with this though is then that if your object has like sharp edges, and those should be casting shadows on themselves, then sometimes you get what's called light leakage. Light leakage. Okay. Light leakage, typically, like if you can imagine, we're trying to render a column. Okay. Okay, and we're having a lot of errors over here. So let's just say we should have some kind of shadow like this. Okay, the shadow should start over here, but if we add a bias, then it has a tendency to move the shadow back. And then it looks like, well, we might see it back here too. It looks like light's leaking because the shadow map thinks it's closer, it thinks it should be lit, and it's not really. Okay, so I spent a lot of time talking, and so now I want to spend a little bit of time showing, because there's a lot, like I said, there's a lot of nuances with shadow maps, and even nowadays, there are huge problems. There are huge problems. Okay, so let's take a look at let's take a look at some shadow mapping code. I want to go up here, over here. Okay, I'm going to go and start up. Wrong one. All right. So I have over here a scene with a few different objects. Okay, and I wanted to try doing a few different things. Okay, so the initial thing, I guess, I might have to turn off the lights down a little bit. Can everybody see that? Okay, and okay, so I guess first things first, what do you see in this image? We're talking about the shadows, but what do you notice about the shadows in this image?
They're kind of jaggedy.
Yeah, they're kind of jaggedy. So we have a resolution issue. In fact, I put in a few different resolutions on here. This is a 64 by 64 shadow map. Okay, so this is a very low resolution shadow map, but this is, I think, it helps illustrate some of the issues that you run into. So remember I mentioned that we have this bias issue, right? Where objects that should be, and let me okay. Oh, come on. Here's a good one. Okay, remember I said you were going to see these like stair stepping. Technically, this is lit, right? This side of the box is lit, but because the way the light's hitting it, we can see exactly when it thinks it's in shadow and when it's not in shadow. So even though this same box was rendered into the shadow buffer, we're having issues because of the numerical precision. All right, we probably set the near plane too close to the light, and that's probably part of the issue. Okay, so one way we could deal with that is to just add a bias to it, right? So so this little button will increase that value for epsilon. So if I hit this button, we see we got rid of most of it on the floor at least, but we didn't really get rid of it on the box. So let's do it some more. Okay, it's almost gone. But if you notice, the shadow on the bunny disappeared, the ears. Okay, now it's completely gone, and now we're starting to lose some of the shadow off this little torus knot. Let me increase the resolution real quick to whatever I think the max is. This is a 2048 by 2048 shadow map. Okay, so we're going to just play with the bias some more. Okay, so this is like no bias. This is what happens if you have no bias at all. All right, which I'll admit looks kind of cool. We're gonna watch this for just a second. I think I'm asking the GPU to do too much. Let's turn that down a little bit. What is it doing? I think it's because I'm streaming. I think it's must. This is not a difficult thing to render. Okay. I'm going to toggle the animation off. Okay, so does everybody see what I'm talking about when I'm talking about bias? You can really see the inherent issues with the depth buffer in this case. Okay, so the higher the accuracy of the depth buffer, the better it's going to be. With WebGL, I know you're limited, or sometimes you get a 24-bit one, which is nice. Sometimes you get lucky and get a floating point one, even better. But in this case, we have a 16-bit one. Okay, so let me toggle the resolution up a little bit. Okay, so yeah, if we play with the bias, just having a small bias helps out a lot. But I think, like I mentioned, sometimes you can start losing detail. Okay, let me pause it right there. So let's look at the bunny, and let's see the effect of the bias on the bunny. As I increase, you can tell that some of the shadow, the casting the shadow from the back of the ear is you're starting to lose some of the shadow on the bunny's ears. Okay, So sometimes it doesn't do very good with things that are close by. And this is technically light leakage, right? Because this should be shadowed, but it's not. It's like we're letting light leak through the object. Okay, so this is that term, light leakage. Because it should be shadowed, but it's not. Okay, so the more we do it, and you can even see over here that a small bias can have big problems. So over here, obviously we have no errors at all. That's pretty good. Okay, so you do some tweaking, but I think really depends on what you're looking at in terms of, you have to kind of understand your scene. All right. So that's the first thing we can do. Now, what's another thing about the shadows? What else do we notice about them? So we mentioned jagged edges, right? We mentioned the bias as an issue. What else about the shadows? Are these realistic shadows?
No, they're hard shadows.
Hard shadows. Okay. So shadow maps, I guess initially, right, don't get you soft shadows. Like that would be nice. That's one thing with path trace images. When you allow all those extra bounces of light, you can allow some like soft shadows because that's a little bit more realistic. So that's let's take a look at how that gets done. Turn on the light just a little bit more. Sorry, I wish it would fade like the eLife building. They have a program where it's like it's easier on the eyes. Okay, so minimize. Okay, so the next thing we can do is called percentage closer filtering. Okay, now this has a little bit more of the shadow mapping code that I wanted to show you. So over here we have our shadow coordinate coming in. Whoa, I'm never going to get unused to just double clicking. Okay, so remember we calculate our shadow coordinate. That was the shadow, the bias matrix times the light projection matrix times the world matrix and so on. So remember we were talking about the pipeline. You have to divide by Z. Remember that's how you project. Okay, so this is that step over here. We're projecting. So we are dividing over here by W. So after you do your projection, you can divide by W. And so now our Z coordinate, so P, this represents the Z going from 0 to 1. Although because we're doing it from the perspective of the light source, if the far plane of the light was closer than the object we're trying to render, then technically that value would be greater than 1. And if let's say the object we're trying to render was closer than near plane, that would be less than 0. Okay, so because normally what happens before it gets drawn in the frame buffer is then the clipping step happens. So values are clipped between 0 and 1, but that doesn't mean that's going to happen over here. So in these simple examples, we're probably saying, well, we're always going to make sure that the shadow receivers are inside of the volume, right? But ideally, you probably only want to put your shadow map so it tightly encloses the shadow caster, because that's where you want the detail. Okay, and then the shadow receiver is kind of a secondary issue. Okay, but over here we do our projection, so we're getting our XY coordinates and our Z coordinate. And what we do with percentage closer, this is where we use that offset. So we say, let's take a look not just at the one value we know we're going to be in, but let's take a look at the neighboring values. And then let's take the average result. So what percentage of the samples nearby our value, I guess the pixel we're checking are also in shadow. Because sometimes that can give you some, it can give you some extra information, right? So like in this example, if you were to take the average, we might be able to say, well, technically maybe over half of them are being lit, so we don't need to say that it's all in shadow, right? But maybe you have edges that you'd like to be able to, I guess, blur. So if you make that offset bigger, then you can actually, it's almost like blurring the shadow map. Okay. Now, when you blur the shadow map, you don't want to blur the Z values. Does that make sense? Okay. So we don't blur the shadow map. We just blur the outcome of the test, whether it was in shadow or not. We don't blur the Z values. That there's a distinction we want to make here. Okay, so in this case, we're asking for 8 samples. One's the main sample, so we don't offset it, and the other one is we go basically all of the 8 corners, right? So we go this one, this one, this one, this one, and these neighboring ones. You could filter it based on, you could say maybe the one in the middle weighs more than the other ones. So you could add a weighting factor to it as well. And there's all different kinds of ways you could do this filtering. Okay. And then over here at the end, I just divide by 9 because I'm just doing a simple average. But there's more ways, and this is something you should play around with. What happens if I say that the main pixel, I multiply 4 on that one, and I multiply, so you kind of like make it radially, make the samples around it less significant, statistically significant. Okay, so let's take a look at that. So I'm going to turn on PCF. Hopefully we don't see anything. I wonder if I can just turn off. Is there a way to... Okay, we'll just go back down again. Okay. So I'm going to toggle the resolution. Let me hit refresh on this page real quick. Maybe I'm just running out of memory. Okay. That works there. So let's toggle PCF on. Now, I'm going to adjust the spread amount. Okay, so if I click the first one, you'll see that now we can see the blur because I'm blurring the results of those neighboring pixels. But I can increase the amount of that offset. So if you wanted, so just as here's off, here's on. If we go really high resolution, you'll notice that offset has less and less effect. But now you see if you wanted a hard shadow, but you wanted the edges to be nice and anti-A-list, then that's how you would do it. Okay. Now, here's what happens if you use a low resolution. You'll notice that we get, because we don't have quite nearly as many samples, it feels like it's been really spread out. Now, that's useful. So I'm gonna increase the resolution just a little bit. Okay, that's off. That's on. Let's increase the bias. I would almost say we use the same resolution, right? The same resolution, but I would argue that that looks better than that. In fact, let's animate that. Okay, and if we turn on PCF, you could probably make do with not quite as high resolution shadow maps, right? If you just kind of add some filtering to it. Or what do you think? From an image quality standpoint, if you are limited to like really low res, because just remember you're rendering these light maps, these shadow maps. So if you render a big one, you're rendering like the 2048 by 2048 one. It gets you a nice high resolution, but at the same time, you just rendered what 4 million pixels, right? In this one, I have a 64 by 64. I only rendered, 4,000 pixels. Okay, so there is a difference, right? So I would say if you don't necessarily need the high resolution, you could just use PCF to kind of help improve. It's almost like it gains you a little bit extra resolution. Okay, so let's increase the spread. I just increased the resolution of the shadow map, but I can really spread these out. Now you do kind of you can tell now that the filter you're kind of getting the pixelation back out because we're looking too far out. So you either have to look at more samples or just increase the size of the texture. So let's increase the I guess that works. I've done it with as many as like hundreds of shadow map samples. But what I think is neat about this is that if you want to have like a soft shadowing effect, then this can get you there. And some ways to improve it are just like jitter the sample so they're not exactly like an even grid. That can help improve the quality there. As you get further and further out, though, you don't really notice the problems as much. So this is one way of improving quality. Okay. Okay, so let me turn off PCF again. Okay, so we looked at resolution, the effect of doing resolution. We looked at the effect of toggling, of using percentage closer filtering. If you set the filter width of the PCF wider or smaller, and the effect of the bias. Okay, now here's what I mentioned that when you're rendering the light map, the shadow map, right? This is technically what you're drawing. So in this image, this is exactly what we're drawing. Okay, so if I flip back, you'll notice that basically all the areas that are black are the areas that we don't have in our map. Okay, so if we go back over here, okay, we also have. I guess I can toggle the resolution here. Let me see here. Okay. So if you're at all wondering, let me adjust this until I think I got it back to. Okay, so there's 0, no bias at all. Okay, so if you're wondering like what the Z buffer is essentially storing, this kind of gives you a little peek. In terms of you don't get that much resolution unless you like deliberately render that much. Okay, so the bias. So if we add a little bit of bias, you see where you're going to get the errors because, and like the bunny ears, right? You have these like curved surfaces. That's going to be a source of error because we just don't have enough. If you put the PCF on, let me. We get rid of the bias. This kind of lets you see a little bit the effect. Kind of get that a little bit of a halo effect in terms of you can kind of see where by taking the average of samples around that you're measuring what's the likelihood of a shadow being here. That's kind of what the switch is. Okay. And then if you increase the resolution, you'll notice that it just gets better and better and better. So that's that's a common I guess that's a common thing that you have to do. Okay, is you have to tweak those parameters. What's the best bias? What's the best resolution? Because like I said, you can have as high a resolution as you want, but then you're rendering like millions of pixels when you can be, maybe you don't need that much, okay? One thing we could try, or what we haven't tried out yet is there's ways of handling some of those errors. So one's called variance shadow maps. So instead of encoding just the Z value. Sometimes what you also code is the variance for that Z, so you can measure how is Z being affected in that area, and you can say, okay, this kind of gives you an idea of it helps. I guess it helps improve quality by storing what you think the plus and minuses are, right, for that depth value. And then another one you could do that I've seen is like use logarithmic space for your shadow maps instead of linear space. Because technically that's what we're doing here is we're using linear space. So if you can kind of encode your shadow map in a way that you can get better comparisons. Another kind is called cascaded shadow maps. Anybody heard of cascaded shadow maps? Okay. Cascaded shadow maps are cool. All right. I think it's a interesting way. So let me just get the lights back on. Okay, so cascaded shadow maps. I mean, what happens if you decide you're going to go for the big open world adventure game, or a big massive scene, right, with mountains and hills, and so you're going to be doing the shadow map for the sun, right? So how big of a resolution of a shadow map do you need so that it looks, I guess, high quality from the viewpoint of a person? You want to take a look at, what's that? You need something ridiculous, okay? So one way to get around that is use cascaded shadow maps. So in other words, you render several shadow maps for different distances. So you might have a shadow map that kind of covers the mountains, and then at a certain point, that's as far as it goes, and so that we have a good shadow map that covers like mountain ranges and so on, and then you kind of build up smaller and smaller resolution until you're where the position of the player is. And then that way you can have a nice, small, high-resolution texture map, shadow map. So I'm going to erase this real quick. Maybe I could search for an image. Cascaded shadow maps. This one might have a good okay, so here is what can happen, right? Is you get, because you're making this choice, well, how, should I render a wide field of view for the light map or a narrow field of view? So instead of just rendering, like I said, one set of shadow maps, because this is what you have over here, look at all this wasted space, I guess. You'd like to have higher resolution, but you basically partition the frustum into several areas. So you have like a far away area, a closer area, and so then you render basically 3 different shadow maps for different resolutions to capture the view frustum of the light. And this helps get rid of some of this perspective aliasing. Remember, this is perspective aliasing, where technically the closer and closer you get to being like straight on with you get worse and worse error, because how are you going to know what's near and far? So you partition it, and then you can orient the scene in a way that you can kind of get the best results. So this works. What you do is you take your entire scene, you subdivide it, and then you render those sections off with a different shadow map. It helps improve the accuracy. And then that way, when you're let me zoom in. That's a good image right there. The colors tell you which shadow map is being used. So you can tell that if you're in the green area, you're getting a different, higher resolution shadow map, and versus back here, we're getting a different one. Okay. That can cause issues like seams. So shadow map is like a constant battle between image quality and performance. Okay, so then you have these things like, okay, this helps improve quality overall, but then you have these seams on, like, you know, where you decide I was going to draw one shadow. So then you have to like fix that problem. You're always trying to fix these little, it's like a bunch of leaky pipes. You got to fix one pipe, another one starts leaking. You're like, okay, let's go tweak it over here. PCF, yep, that's I think depth bias. Remember I was telling you about light leakage, and you know, you have these issues going on here. Erroneous self shadows. Another way of improving quality. There's light space. Okay, so anisotropic filtering. We talked a little bit about that last time, where it helps improve the quality. Light bleeding. So this is what it should look like, but then this is what actually happens. You get this light leakage. Okay. And this is even with some of the more advanced algorithms. Okay, then you can combine them, and that's the other thing, combining light maps with different ones. So I think we're just about out of time, but the one, I guess the one big piece that you can take away from this is that if you can constrain your light map to just the objects that need it, or the better the quality is going to be. So one AAA game, their main approach was, well, we are going to render a nice big shadow map for the main character, and then because that's where the player's eyes are going to be looking at most. And so you have a nice high quality one for the character, and it looks like, oh yeah, you know, it's doing, he can cast really high quality shadows on the ground, but you don't necessarily need to cast high quality shadows for everything. And that's the thing, is if you want everything, then you just have to make those choices. But it's all about tweaking. Which setting is going to get me the best view? Can I constrain my light map to just only the objects that I really need it? And then you can use things like cascaded shadow maps to, let's focus the shadow map in certain areas of the scene where we can have the resolution. It helps combat some stuff. But anyways, so yeah, anyways, the hybrid topics on Thursday will be about shadow volumes, which is another important technique. You get nice high quality shadows with very little errors, but they can be CPU intensive because you got to calculate these shadow volumes. But okay, yeah, and then if you have any questions, just come talk with me about the homeworks or anything like that.